Hey everybody, we're going to continue on with chapter 2 today, talking first in this section about hybridization and hybrid orbitals. So for some of you, this might be a little bit of a review, but generally I want to get just the basic concepts of hybridization down. So some reminders here when talking about hybridization. Generally, we're going to be talking about the idea of a bond using the valence bond model. And we're reminded that when atoms are involved in a covalent bond, when they're sharing electrons, we're interpreting this as clouds of valence electrons that are being overlapped or shared. So the valence bond theory again describes a covalent bond as an overlap of two filled orbitals. So we think of the singular orbitals. Remember, we talked about those in chapter 1 and their electron density. And a bond, a covalent bond, is the overlap of these two orbitals. So for example, in H2, each hydrogen has a s orbital, and the covalent bond is formed from the overlap of these orbitals. When we have a bond like this, a overlap of s orbitals, that is called a sigma bond. Generally, we can also refer to this as a single bond. So a sigma bond, again, overlap of s orbitals via a covalent bond, which is a single bond. So again, reminder, single bond is the sigma bond, and it has this cylindrical symmetry that's shown here with the orbitals. But if you have multiple bonds, like a double or triple bond, you actually are going to be using p orbitals instead of the s orbitals. And the overlap of the p orbitals we call a pi bond. And these p orbitals you can see actually occur. We know that the normal p orbitals are perpendicular to the bond. So this would be the normal p orbitals, and you can see they've formed this overlap on the top and bottom to make a pi bond. So this would be one pi bond formed by p orbitals. So for molecular orbital theory, we know that as electrons occupy atomic orbitals, they similarly occupy these molecular orbitals. So these overlapping orbitals when you form a bond. So in a single atom, they have their atomic orbitals. That's in an atom all by itself. But when we form molecules, when we form bonds, electrons inhabit these shared density areas, these bond areas, in a similar way with similar properties as in a single atomic orbital. So some things we know about molecular orbitals is they can be talked about as three different types of orbitals. We have an anti-bonding orbital area, which is a higher energy area, higher energy than the original atomic orbital. Non-bonding orbitals, this is atomic orbitals that are not involved in bonding. So we know that sometimes electrons, for example, on oxygen, we know oxygen, if I draw oxygen out right here, has two sets of non-bonding electrons. These electrons usually do not participate in bonding, and so they live in non-bonding orbitals, electron density orbitals that do not participate in these bonding orbital regions. And then we have the bonding orbitals, which we just discussed. These are lower in energy than the normal atomic orbitals, and there's density between the bonding nuclei. So electron density that exists between the two atoms that are involved in the bond. When we discuss how many molecular orbitals exist when we form a bond, it should be equal to the total number of atomic orbitals in the original atoms of the molecule. So, for example, our example of H2, each hydrogen atom has one electron in the 1s orbital. These are the original. So when they come together to bond, they should have two bonding orbitals in total. And we're going to talk about that when we look at hybridization. But again, the number of atomic orbitals going in should ultimately equal how many, not the kind, but how many of molecular orbitals there are in the resulting molecule. So valence bond theory suggests that bonds are derived from an overlap of atomic orbitals, as we just talked about. However, there are some inconsistencies when we originally think about this. For example, we just talked about the tetrahedral geometry of orbitals in things like methane. But we don't understand, or we didn't understand, how the overlap of s orbitals and p orbitals can actually form the correct geometry. So we know that we actually form this tetrahedral geometry where all of the carbons and hydrogens are at angles of 109.5. However, if you originally just thought about carbon making bonds using its natural s and p orbitals, you might think that it would form bonds along the p orbital directions. So the x, y, and z positions of the p orbitals, and then maybe have some other bond using its s orbital. And this might make you think that the bonds would be at 90 degrees with some other arbitrary angle, maybe at 135, using its s orbital. But we know that this is not the case, and instead it has 4 orbitals, bonding orbitals, that are at the same distance from each other with the same properties. So how does it do that? The theory of how it does this is via hybridization. So in hybridization, we know that none of the bonding orbitals in methane are actually 100% S or 100% B. And instead, they form hybrid orbitals that have a little bit of characterization of the S and a little bit of characterization of the P. 3 of the p orbitals in carbon and the 1 s orbital actually hybridize together to form this tetrahedral, forming 4 hybrid sp3 orbitals. And again, these are arranged in a tetrahedral around the carbon. So each of the 4 hybrid orbitals ends up having about 25% of the S character and 75% of the P character. If you look at the bottom here, you can see that's because 1/4 of the orbitals that end up are coming from the S and 3/4 are coming from the P. So again, these combine together. This is the initial state of carbon. But we know when it forms bonds that it hybridizes its orbitals to form 4 sp3 orbitals that can then bond with the hydrogens. So again, the idea is that this is happening during bonding to the carbon atom specifically. Okay, so again, this is just a pictorial view of what those sp3 orbitals look like. Again, we're taking the 3 p orbitals and our 1s orbital and blending them together to make 4 sp3 orbitals. You can tell they get their name sp3 because it's made of an s and 3 p's. And then these orbitals, if you can see, here is a methane right here. So the carbon atom is in the center, and it's using its sp3 orbitals. This is an sp3 orbital, and this is one, and this is one, and this is one. And it is forming a bond with an s orbital of hydrogen. And that's happening on each of these ends here. So we can mix orbitals in different ways to fulfill different bonding situations. So if we mix 2 s orbitals with 2 p orbitals, we obtain 3, excuse me, I said 2 s orbitals. If we combined 1 s orbital with 2 p orbitals, we get 3 sp2 orbitals. And we get 1 orbital left over, 1 non-bonding orbital, or a orbital that can participate in a different kind of bond. A p orbital is left over. When these sp2 orbitals are filled with electron pairs, the bond angle that results in this case is 120 degrees apart, and that's what we call the trigonal planar. Remember when we talked about having an element with 3 bonding pairs, it forms this shape of a trigonal planar. This is shown in 2 ways. You can see here they're showing the paper in this direction with the trigonal planar arrangement being here. An sp2 is again made of 1 s and 2 p orbitals, ending up in this 3 sp2 orbitals and 1 p orbital that is unhybridized. These unhybridized p orbitals can actually still participate in bonding, and they participate in a way to make a pi bond. Remember that pi bonds are an overlap of p orbitals. So up here in this example, I know this looks a bit complicated. There's a lot going on, but what they're showing is this is a carbon here, and it is sp2 hybridized. So the green orbitals are its sp2, it's 3 sp2 hybrid orbitals right here, here, and here. You can see one of those orbitals is going to form a bond with a hydrogen. Another orbital is forming a bond with a hydrogen here. Another orbital is going to form a bond with this carbon next door that is also sp2 hybridized. And you can see the same thing happening over here. Great, so all of these sp2 orbitals are forming single bonds all around, single sigma bonds with their respective partners. But we have these p orbitals, the p orbital that is left over in each of these cases. That's represented by this red and blue orbital going up and down. Remember, p orbitals have this shape. And those p orbitals on either side are going to form a pi bond. That's shown, represented here. So sp2 orbitals have this ability to make pi bonds using their leftover p orbital. And so normally you see sp2 orbitals when it comes to carbon associated with double bonds. Now, our last case of hybridization is sp hybridization. That's if only one p orbital hybridizes with an s orbital. This gives us just two orbitals that are called sp, two sp orbitals, and they are separated by 180 degrees, right? When we have two orbitals like that, they will form 180, a linear structure. Again, we call this arrangement linear, and each orbital has 50% S and 50% P character, as you would assume. In this case, when we form our SP, in the case of overlap, you get two SP orbitals, and you have two unhybridized p orbitals that are left over. Depending on the atom, again, these can contain electrons, or they may just be empty unhybridized p orbitals. Here's an example here. You can see this beryllium chloride is forming bonds with chlorine using its sp orbitals. Here is a sp orbital, and here is another sp orbital. Now, the other orbitals that are shown are unhybridized p orbitals. It gets a little bit dense here, but remember, a p orbital has a full shape like this. So one of these p orbitals is this one, and the other one is kind of coming in and out of the page here. So two p orbitals that are unhybridized, and again, these can or cannot be filled with electrons to be used for further bonding. And actually, in the case of carbon, these p orbitals are filled and are used for forming further pi bonds, just like in our sp2 case. So again, I know this looks a little bit complex, but in the center of this molecule is a carbon. And you can see in green is the hybrid orbital. Here's its sp orbital. One of them is forming a sigma bond with this hydrogen, and the other is bonding with its neighboring sp hybridized carbon. And all that leaves are the unhybridized p orbitals, which for carbon would be filled with electrons. Remember that carbon's valence electrons look like this. So this is an S, here's P. So when we make an SP, we have 2 and 2. So 2 SPs and 2 in the P. So each of those p orbitals has an electron in it. And you can see this is what the p orbitals look like when we kind of take away the hybrid orbitals. Again, one is in this direction here, and the other is kind of coming in and out of the paper. And they form 2 pi bonds. This is the case when we have a triple bond. Now again, this situation, if it forms a triple bond, if it forms two overlapping pi bond, is key to how many electrons are in this unhybridized p orbitals. If there are no electrons here, if we change how many electrons, even if it's carbon, and we remove or add electrons, that will change its ability to form these pi bonds, because the pi bonds need to have a single electron in p orbitals that then overlap with another neighbor in the same situation. Now that's a lot on the theory and when you may see these structures, but a shortcut for organic chemistry to determine the hybridization of an atom in a molecule is this. What you're going to do is, number one, look at the atom of interest, whatever that may be, if it's a carbon or it's a chlorine or it's a hydrogen. You're then going to count the number of atoms connected to it. That's key, atoms, not bonds connected to it, but atoms. So if you see something like this, let's say I want the hybridization of this carbon, remember that it has 4 atoms connected to it. It has 3 hydrogens and 1 carbon connected to this atom. Okay? Next, you're going to count the number of lone pairs attached to it. So you can give an example of that. Let's say I have this situation. I want to know the hybridization of this oxygen. This oxygen has 1 atom attached to it. And it has 2 lone pairs. So its number would be 3 in total. You're going to add the number of atoms, the number of lone pairs together. You'll get your number. In this case, it's 3. In our earlier case of a carbon here, this was 4 because it has 4 atoms attached to it. And that number is going to be used for the hybridization. If you have 4, it's sp3. If you have 3, it's sp2. 2, it's sp. And if you have 1, your atom is probably just hydrogen, and it's just using its s orbital. That's because hydrogen is pretty much the only thing that doesn't have any lone pairs, and it will only make 1 bond. Okay, so let's do a practice of this to kind of practice identifying the hybridization of an atom. Remember, the key to the hybridization is all about how many atoms it's connected to and how many lone pairs it has. So here's a carbon that has been starred, and I want you to identify its hybridization. In this case, remember in our line dot structures, we know this is the carbon. It's attached to a carbon here and here, but don't forget, we don't draw hydrogens in our line structures. So we should know that this carbon is also attached to 2 hydrogens. So this carbon here has 1, 2, 3, 4 atoms attached to it, making it sp3 hybridized. We can do another example on this same structure. Let's try this carbon right here. Here is a carbon. Notice this one is involved in a double bond. This carbon has a carbon attached to it here and a carbon attached to it here. Now remember, again, we're not showing hydrogens, but you should know that carbon makes 4 bonds. And double bonds count as 2 and triple bonds count as 3. So this carbon is already making 3 bonds, which means there is 1 more hydrogen here. So again, let's count. It's attached to 1, 2, 3 things, which makes this carbon here sp2 hybridized. And if you go back in the slides, you'll notice this makes sense. There is a double bond involved, and sp2 is usually associated for carbon with double bonds. Okay, well, that is it for hybridization. We're going to move on from here to next talk about alkanes.